I'd like to just welcome everyone to VersaPile's Helical Piles Foundations for Engineers and Building Professionals. We'll start off, after a brief introduction, we'll touch briefly on the history of helical piles, and then we'll talk a bit about the practicality and just how they compare to more conventional piles. And then we'll talk about the lifespan of them and the limitations of helical piles. And we'll go into a brief discussion on what to look for in a helical pile contractor. So let's start off talking about who is VersaPile. We're a helical pile contractor. That's all we do. 365 days a year is we put helical piles in the ground. Anything from smaller light loaded structures like in the residential sector to like small commercial light industrial types of uses, and going on to like larger commercial ones. So we're a Deep Foundations Institute member, and we basically source our piles from 3 different suppliers in Canada. And we've done about 30,000 leads in Manitoba, so we're pretty experienced in the Manitoba market. Like I said earlier, we're just a contractor, so we're sourcing our piles from our suppliers, and we're kind of fancy ourselves like a pile broker. We're going to bring in the piles that make the most sense for our clients out of the different suppliers that we have. So I'd like to touch a little bit on the history of helical piles. So they were first invented in 1828 by Alexander Mitchell. This is prior to steel being mass produced. So we've got probably would have been wrought iron piles. The helical on his initial invention was 48-inch diameter. And again, it would have been wrought iron. So this thing would have been fashioned by basically bashing or extruding the shaft. It was installed by hand. There would have been a crew of anywhere from 20 to 30 people installing these piles. And the first installation of them was for a lighthouse. It was in the UK on the Thames River. They installed the lighthouse. This is a significant, invention for the time, because up until that point, unless there was rocks near the ocean, there wasn't going to be a lighthouse built there. So helical piles were formative in marine structures because they allowed people to build in cohesionless soils and clay soils. So Alexander Mitchell actually was quite in demand through the early part of the 1800s. In 1855, he was shipped over to the US, and they built 100 lighthouses on the eastern seaboard using helical piles. Lots of structures all across the world, specifically marine, mostly marine, were built on helical piles at the time. So through the 1860s, this is an example. This is still in existence. Just to show you the worldwide kind of reach of helical piles, you've got the Beachport Pier in Australia that was built in 1878. And it's, I think, one of the longest piers built on these type of piles. It went 4 kilometers out into the ocean, and it exists this way today. I think it's a little bit shorter because in the 1970s, a hurricane took it out on the far end. So you can see that helical piles was on a pretty big growth curve until about 1890. And I think this is where there's often maybe some drama associated with helical piles, like, oh, they must be out of use because they failed. Well, part of the reason of their decline in popularity was because of this machine. So it was easier to use steam engines to build something that could mechanize installations, and using a simple steam engine to drive a heavy weight to pound in timber piles was way easier than having crews of 20 to 30 people turning in big awkward steel piles. So that's basically what started to lead to the decline. And in 1909, the Frankie pile was invented, which is kind of like the grandfather of the cast in place pile that we use. And it wasn't until 1950 that popularity of helical piles started to increase. Basically, the hydraulic motor made it possible to put a lot of force. And in the 1980s, this was further developed so that really small machines could get in and apply quite a bit of torque to a screw pile and be able to turn them into the ground. So in the 80s, you see a lot of their use in residential markets. And fast forwarding to today, they're gaining a lot of acceptance in the commercial segments, especially where there's tricky soil conditions. So this is an excerpt out of Piling Canada's Q1 magazine, and it's talking about a 32-story building in London, Ontario, that was built on helical piles. So a common question I get asked is, so where do these fit, and how do they fit into construction? We have conventional, like in Manitoba at least, the common conventional piles are cast in place and driven piles. Obviously, cast in place are being used residential market into the commercial market, but on lighter structures. And driven piles are kind of the go-to for when there's tricky soil conditions and when the loads are starting to creep up there. But I find that the easiest way to kind of see how helical piles kind of can fit is by looking at the interaction with the soil and what you need to do to be able to increase or decrease the capacity of the pile. So in cast in place, it's pretty obvious you just need to increase the size of the pile or potentially the depth of the pile to get a larger load. So you're looking for that interaction with the surface area of the pile to get your load. In a precast driven concrete pile, there's usually about three sizes, and they range in capacity anywhere from about 1,000 kilonewtons all the way to 1,800-ish kilonewtons. And there it's just, you're adjusting the size to hopefully get down to a really dense strata like the till or maybe even bedrock. And steel driven is similar, except that often there's less surface area being exposed to the dense layer. So these are often the most expensive pile type in the driven sector, because you probably will punch through the till, and maybe you want to, depending on the load that you're looking for. But you can obviously change the aspect ratio of the pile as well as the weight of the hammer. The steel helical piles are a little bit more complex, so that's why it's not just a simple answer exactly where they fit. With the steel helical pile, you can have an adjustment with the helical, so you're changing the area that's available to the soil, clay, and you can also change the shaft diameter anywhere from 2 inches to 24 inches. And if that's not enough adjustability, you can also adjust the number of helicals that are added to a pile. So there are some stipulations on there. You want to keep those diameters at least 3 diameters apart. And you want to make sure that the topmost helical, you could put 10 on there if you wanted, but you want to make sure that that topmost helical is below frost. Another important part of steel helical piles is just that you hear me saying helical instead of screw piles a lot. The reason for that is a helical pile should be engineered, and it should be made out of new materials with good welds. And you want to have the flight opening between the leading edge and the trailing edge of the helical pile to be no more than 6 inches. If it's greater than 6 inches, that makes it a ground anchor. And if it's an inconsistent pitch along the helical, along that bearing blade, then that's what makes it a screw pile. Another thing that helical piles are different from maybe screw piles or ground anchors is that they're going to have a 90-degree angle at the trailing and leading edges of the helical. So we kind of have half answered the how do they fit. For Manitoba, we kind of break it into low capacity and high capacity screw piles or helical piles. So low capacity piles would look like a single helical pile in Winnipeg clay on a 16-inch helical. That's going to get you about 30 kilonewtons ULS. If you're looking at a double helical, it's going to be around 70 kilonewtons. That's probably going to be a bit of an understatement, because there's a cylindrical shear model that will probably contribute to the pile, but we're basically modeling it on a reaction force from the clay to the bottom of the pile. So it's an area, more or less an area calculation. For when we're designing these piles, we're quite comfortable using the torque correlation factor. So it's an empirical formula. It's basically saying that the ultimate strength of the pile is equal to a fitment coefficient times the torque that gets applied to it. It's a simple kind of model, energy in equals energy out. We use this in conjunction with limit states, and we find that it does a really good job of understating the ability of the pile to resist a load. Now, if you want to get a little bit more into the weeds, KT, the fitment coefficient, is equal to lambda over the diameter of the pile to the power of 0.92, where lambda is a fitment constant. Again, this is an empirical formula, and it's really meant for and suited to piles like 4.5 inch and lower is where it kind of performs best. You can still use it above that, but the one thing I will point out is that, so I'm giving values at the top of this page for Winnipeg clay, which is pretty much the worst place that you're going to find clay in Manitoba. In cohesionless soils, you can have performance much greater than that. So moving on to high capacity helical piles. This is where you're going to see loads, you could put loads in excess of 400 kip on piles, on high capacity screw piles. And we've gone as deep as 26 meters or 118 feet. But here we're basically looking very similar to a driven pile. We're looking for that end bearing capacity, and it's going to be in till or on bedrock that we're kind of aiming to stop it at. The difference in design for these ones is that we're looking for geotechnical directed capacities on these piles. So we're looking kind of to the experts in the area to tell us what their experience or expectation is going to be for that pile. When we're designing them, we are looking to the torque equation for installability and for quality control, but we're not going to use it to predict the performance of the pile as much as we're using it for just making sure that that pile is going to be able to get through all the different layers of the soil, especially when you're going down 26 meters. There's a lot of variability on the way down, and we don't want to shear that pile, and we don't want to create other problems. We'll look at that in the limitations series section here. So a common question when we're dealing with clients is like, how long will they last? And unfortunately, I don't want to sound like a lawyer in every section here, but there's the engineering long answer to that question, then there's the simple answer. So the long answer, we're at the DFI Helical Pile and Tiebacks conference in Ohio. That was last summer. And they had a presenter come on, Marilyn Lewis. She's a professional engineer, and she specializes in corrosion resistance. And what she said is the potential for corrosion is actually a function of the electrical circuits that are happening on any building site. And the building can be the cathode and the pile can be the anode, or depending on what's at play, you can actually have the building being the anode and the pile being the cathode. And it's really not an easy answer. She was giving an example of one site where they took, I think, a year to analyze the entire process to see what the building's resistivity was and what the pile's resistivity was. And they're trying to, optimize their formula to make sure that they end up with the least corrosion possible, or at least be able to size things accordingly. The whole thing is made even more complex by the fact that if your anode increases in size or your cathode increases in size, it's going to change the whole reaction. It might even flip the whole equation around. So we're kind of practical guys here, and we like empirical data if we can find it. And the US did a lot of studies. So the National Bureau of Standards in the United States, they went out and put 1,000 sections of steel driven into the soil all across the United States. And they measured and recorded the corrosion. They did it in marine environments. They did it in just a standard field. They did it with all different types of soil. And they went back after a period and measured and recorded the corrosion rates. And that gave them a table. So kind of summarize it to kind of our rules of thumb. Obviously, if you've got more moisture in the soil, you're going to have a greater potential for corrosion. That's all about, for steel, that it's the availability of oxygen across the steel that leads to corrosion. So as well, another rule of thumb is that the thicker the shaft, the greater the lifespan. And the other rule of thumb is that hot dip galvanizing adds anywhere from 2 to 2.5 times the lifespan. So prior to this talk, I talked to Mark Pietrus from Vulcan Galvanizing, and he was kind enough to say that I could put his information up on the screen. If you want to talk to someone who's an expert in galvanizing and figure that stuff out and get a little bit more into that, you can feel free to contact him or contact me afterwards, and I'll share his contact. So sorry, just back to that for a second. One of the things that we've found that's been helpful and adds value to our clients is that we'll galvanize everything under or 3.5 inch and under for shaft diameter. Anything that's 4.5 and greater, we basically give that option to the client. And the reason for that is a hot dip galvanized 3.5 inch pile in our clay, which is moist clay, which is kind of on the moderate to highly corrosive side, it's going to last about 89 years. A 4.5 bare steel in that same soil is going to be 69 to 89 years. So that's because that 4.5 has quite a bit of thickness. And as you go up in shaft diameter, the thickness is also increasing. So onto the limitations. So the three limitations that we're usually looking for in designing a helical pile is the column strength. Fortunately for us, this is something that we have experienced relates a lot to the amount of torque that we're putting in. So what I mean by that is if we're searching for a certain load and we want to design a pile around that load, we're going to use torque as quality control at the very least. So we're going to make sure that that pile has been sized so that it can handle the torque that we're going to throw at it. And fortunately, torque is a function of shear, and column strength is also a function of that same kind of cross-sectional area. So the two of them end up correlating pretty well. So if it's been designed to be installed to a certain torque and there aren't some other conditions at play, the column strength is going to be there. So this is something that we can kind of pre-check, and we already know what piles are going to be suitable for what loads. So we don't get into a situation that we're going to be stressing the pile in the column strength category. Something that's a little bit tougher to design around is the lateral capacity. And the reason for that, it's more of a function of the soil than it is the pile. Obviously, you can put the pile into deeper depth and then turn this relationship into more of a bending moment question, but it's really the soil that's on the opposing side of the lateral force that's taking the brunt of the force. So the solutions here are, if we're see the little white circle there, we're looking down at the top of the pile. If we increase the diameter of the shaft, that's going to make it so that we're going to actually get an exponential increase on the lateral capacity of that pile. The other thing that we can do is we can add stabilizing fins or increase the surface area that we're exposing. And another option is pile caps. One thing that we're always going to look at as well is the bending moment. So here, as in this example, we've kind of showing the more transparent pile in the background is kind of the original case. So if there's eccentric loading or a large lateral load near the top of an extended pile, that's where you're going to get this bending moment. Bending moment's usually going to be below the soil. And again, that's assuming that the soil is somewhat soft definitely at the superficial kind of area. So when we find that that's true on most sites to about a 2 foot depth and maybe even 5 foot depth, depending on the soil. One of the ways that we've been able to overcome large bending moments is by having a grillage. In this example, the client had a 200 foot tall communication tower and they couldn't put guy wires on it. So I think the overturning moment on this thing was over 1 million pounds per foot. We were able to kind of extend that out to 6, 8 5/8 piles that only have a bending moment of about 40,000 pound-feet. So that's kind of an example of one of the ways that you can kind of overcome a big problem like that. Moving on to talk about what to look for in a good contractor. So I think the easiest thing for us to talk about is the things that we find are important. So we have a staff that's committed to getting things done right. That starts right from the sales side of things, making sure that we're giving people good recommendations or recommendations of whether screw piles fit for them or not. We can do our own internal shop drawings, and we have a strong knowledge of soils. Another thing that's important for us is using third-party engineers. So we use the third-party engineers to verify our designs, and then we partner with third-party engineers like geotechnical engineers to gain expertise in areas that we're uncertain. We have a great install team. So these are some pictures. We've got 3 field supervisors that are phenomenal. They're very experienced. They're experienced in construction as well as in installing helical piles. And then we can have as many as 6 crews going. Proper equipment, I'll spend just a little bit of time. Probably seen a lot of, in all of our pictures you saw that we're using excavators. There's a lot of people out there that are using skid steers. And I'll just kind of pinpoint one of the problems with skid steers. We have skid steers as well, or we have one skid steer. We use it for lighter capacity mostly. The problem is that helical piles are, especially in Winnipeg, to get them below frost, you need them to be fairly tall. At least 10 feet is what we like to use. Right off the hop, you're not going to get your drive very high with a skid steer. So often contractors will put a jib on their skid steer to get that up high enough for them to be installed or to install a larger section of pile. The problem with the skid steer is that the center of gravity is pretty close to the back of the skid steer, and the pivot point or the moment arm is also at the back. So you've got a pretty long span from the back of the skid steer to the drive. So let's say this is a 7,000 pound skid steer, and we'll be conservative and we say it's only 10 feet to the drive. This thing's only going to be able to put about a 700 pound downward force on that pile. Even though it has hydraulics that can assist it, all that's going to serve to do is basically lift up the front of the machine, and you're not going to get a very good crowd. Using a large machine, especially when we're going in a high capacity pile down to till, we've found it's been pretty crucial. So I think it was even at this site where we were testing a Cadillac of skid steers. It had a telescopic boom. We thought it was going to be great for putting in piles, and we just didn't like the way that it ended the install. We weren't super confident. So we load tested the pile and we found out that there was deflection there. So being kind of suckers for doing it right, we decided, hey, we've got to get out there with a bigger machine and see what happens. So we put a big machine on it. We pushed down really hard on the pile, and we ended up getting it to go another 4 feet. And we got the torque that we were kind of hoping for and looking for. And then we load tested it again, and it performed great. So the reason for that is, even though this is a bigger, heavier machine, and it's kind of further away, but when the pile gets down to proper depth, this can actually be quite close to the front of the machine. And we've measured basically in excess of 15,000 pounds. We have this gets into another thing of using the right equipment. We have a ProDig and Teletorque. The thing that we like about it is that we can do things like measure the force down on the pile, and we can also broadcast to an engineer who's on site for quality control. We can broadcast right to their device from that machine, so they can have a really transparent view of what we're doing. So this kind of touches on the proper technique to install. You want to install the pile with downward force. You don't want to have so much downward force that you're exceeding, like a pile with a 6-inch blade opening should be proceeding at about 6 inches every revolution. So you definitely don't want to be putting so much force on it that you're exceeding that. And you're going to want to turn it in slowly enough that you're not augering the soil on the way down. And we definitely want that helical, as I touched on before, we want that helical below the frost line, so that you don't get frost trying to jack this pile out of the ground. So a good contractor should be able to perform a load test if one needs to be done. Either, the site didn't react the way that you thought it would, or there's some uncertainty about the capacity of the pile. Something that we're looking ahead to do, we're hoping to partner with some local geotechnicals or maybe one of our suppliers to help us kind of get over the curve on PDA testing. The easy part is making this machine. The hard part is having enough data with static load testing to have the PDA testing mean something. The reason for that is it would be great from a quality standpoint to be able to not have the clients have to spend $10,000 to $15,000 to do a static load test. They're a little bit more on the expensive side. So, and then any good contractor is only worth the projects that they've worked on. So we're always looking to collaborate and work with engineers on projects so we can be part of the next interesting project. That's the end. So we can kind of open up to, you turn your mics on and your video on, and we can do a question and answer period here.
Anyone have any, concerns about helical piles or hesitations around helical piles that we might be able to talk about? I always certainly a helical pile is not a silver bullet, and I think you covered a few times where that's the case. I always like to hear about the hesitations that people might have so that we can talk about those. And sometimes there's good reason to have hesitation too. So I think that one of the things that we're always striving for is to make sure that it's just important that we say no to certain projects than to find solutions for others, for our reputation long term, right? So I think it's always great for our audience to also hear about the limitations and know when to walk away from helical piles.
Yeah, for sure. So, I'll open that up to the group first, and if I'll wait maybe 30 seconds, and if nobody has any specific cases that they're curious about, then I'll maybe share one.
I'd like to hear if there are, maybe a discussion about, like, we have 2 meters, 3 meters of overburden, like peat moss where we're trying to bridge. And if you run into situations like that, or any places where you wouldn't want to use helical piles, maybe some of those that you've passed on in the past would be nice to know.
Sure. Yes. So one of the areas that helical piles work really well in is when you are uncertain about the depth of overburden, or like you said, you're trying to get from, one layer to another layer, and you need a little bit of feedback on whether you've accomplished that. And that's where that energy in, energy out, kind of using torque to kind of measure as you're going through helps a lot. So definitely a common project that we have here in Winnipeg is using piles where, like, near the river, where we know that there's like really questionable silt pockets or areas where aquifers might even be present. And so we'll go from the surface down through to the dense till, and usually torque up really heavily in that dense till. So that kind of is a similar kind of situation to peat. So, and then I guess on the limitation side of things, or areas that we wouldn't really like to use a helical pile, would be like a really bouldery, rocky, or cobbly kind of area where the sizes of those cobble are kind of bigger than a fist and very frequent. So it's not a big deal if there's a few pieces of cobble or a few rocks here and there. Like a steel pile with a lot of torque on it is going to be able to kind of get past that or move that aside. The problem is when it's all like that. So what'll end up happening is that the cobble or the rocks will just kind of bunch up on the lead edge, and they won't pass through the bearing blade, and then that can pose a problem.
Thank you. I have a follow-up question to that.
Okay.
So it's just in procuring this type of work, there's always a bit of a challenge in bridging from design to construction in the tender process. So I want to know what the smoothest way would be to, say, engage a geotechnical firm in advance, knowing that we might use helical piles in a certain situation. And so the ask that we would make to the geo firm for the testing that's necessary so that our contractor could feel comfortable enough to provide a price for that. Because that's always the trouble, is we do geo for conventional footings, conventional foundations, shallow, deep, what have you. And then none of that ever considered whether helical piles were a candidate even. So I want some text or verbiage to communicate to the geotechnical firm precisely what information we need to satisfy someone that is going to price the work.
Yeah, for sure. That's a common thing that we see here is like we'll get a package. Some contractor wants us to bid on some work, and we go through the geotechnical information, and it has specifications for cast in place, specifications for like a superficial foundation of sorts, usually recommending against it, and then something for a driven pile, but nothing for helical piles. So I guess it depends on where you are in that RFP and how much of a voice you have in that regard. If it's at the selection part of a geotechnical firm, then just asking the question of how comfortable they are with helical piles and if they would consider them for the site. And then to the point of requesting that from the geotechnical firm is another thing, right? So just asking that they make sure that they provide that option. Does that answer your question, Kelly?
I think so. Plus, what you told us today is going to give us more ability to analyze that response that they give us in the geo report.
Yeah, for sure. You can always reach out to a trusted contractor as well, right? Yep. Because they're gonna tell you what. I mean, if they're being upfront and honest and transparent about it, they're going to tell you if they feel that area is a good area or a good candidate for piles. I know one of the slides that I kind of took out just for time's sake was we have some maps of our region, and we know the kind of the trouble areas, and we know where we don't want to do a bunch of work, but we also know the areas that do work and what will work and kind of what to expect from a load standpoint, because we're always trying to do our best. We don't want to give someone a quote, say $20,000 and then come back later and say, oh, we had to add tons of extensions. Now it's $40,000. Like, that doesn't make people feel they trust helical piles.
And can you touch on the stability of the pile, like considerations when we have, like I mentioned earlier, the top layer being peat? There's obviously no significant lateral support there to speak of. And so you can't just go to the bottom of that layer. You have to have some stability in the layer beneath. Can you talk about that a little bit? And that's it for me. Thanks.
Yeah. So we're going to assign a shaft diameter that's going to be able to support the pile all the way from, if we're running through 20 feet of peat, we're probably going to assume that like there's very little shaft friction or even support from the soil along the shaft. So we're going to make sure that that thing is sized appropriately so that we're confident that there's no buckling tendencies or even, we don't want any sway near the surface. So we're taking that into consideration, as well as in the connection detail. We're going to want to look at that side of things, and we're probably going to turn to our third-party engineers to make sure that we get that right.
Thank you.
Dale, we've got a couple that came in with the chat. I'll start with Kelly's. Kelly Eddington is in the solar industry in Ontario, and they've used helicals quite often. They've experienced frost jacking even when below the frost line due to friction on the shaft. How do you deal with that? And I love that this question's asked, because we talk about the solar projects in particular and the effect that they can have on helical piles. So maybe you can address that.
Yeah, so I guess if I was looking at that from a quality standpoint, like let's say we had done that job and someone called us and said, hey, we've got this problem with frost jacking. First of all, I'd be kind of in disbelief at the beginning, because it hasn't been our experience. We've obviously put a lot of piles in the ground, and we have very good track record with it. And I think part of that is that our guys are trained to be very aware of what they're doing in the field. So solar project in particular, there's a lot of piles going in. The tendency can be to want to do that really fast. And one of the things I'd be concerned about is if potentially those piles got installed in an augured situation. So they went in so fast that the soil above them, above the top of the helical, got disturbed, especially if it's going in below frost. The other thing is did we change the area in terms of, like, did all of those piles end up acting like an amplifier fin? I don't know the context of that situation, so I don't know if it's, if there's like 100 piles or if there's 10. But if there's like a bigger number of piles, what can end up happening is steel is a really good heat transfer agent. So you can end up throwing a ton of frost into the ground because that ground is now cleared. You've got all these exposed steel shafts that are, driving that frost down into the ground deeper than maybe what would have been native to that region. So I guess the real answer, in that situation would be that maybe they should have been deeper, but how would you know that prior? Yeah, I don't know if that answers the question, but.
Yeah, it does actually. These projects have thousands of piles, so that's actually a pretty good explanation. I would expect that's what it was. It was fledgling days in solar in Ontario when these were happening, so they had a lot of failures early on. They've sort of figured it out now, but now there's no more industry in Ontario. So
yeah, it's a tricky one. Like solar, we get a lot of solar coming through the doors here as well, or at least we used to when there was more hydro rebates. But the problem with them is that it's very cutthroat. You've got all these other, solar providers, and they all want the work, and they're all trying to clamor over each other to try to get the lowest price. And especially helical piles, it ends up making a significant part of their budget. So often there's some concerns on my side, like you get, them pushing to try to do a 7-inch pile. Well, there's only 3 feet of frost in that field. Yeah, but is that the worst year? So yeah.
That's good. Thank you.
And certainly as your pile shafts get larger, and sometimes with solar, depending on lateral or bending moments that are in play, you might end up with a larger shaft, and add freeze is something that does need to be considered. So we will move into The next question here, what is the size of the pile at 26 meters? Is there installation issue to torque pile that deep? So I suppose like if you're looking at a 26 meter pile, Dale, what are the considerations that you're making to ensure that that pile can be properly installed and that it will support the design criteria?
That's a great question. Definitely that site was a little bit unusual where we went 26 meters. It was in Portage La Prairie, Manitoba. It was particularly tricky because that work was all supposed to be done inside. They couldn't have any disruption of their, it's a food production plant, and they couldn't have any disruption of their plant. They went over, it was mind-boggling the numbers that we would affect if we interrupted things. So they were unusual in that they actually said, hey, we want to go with the smallest pile because we want you to be able to use that machine. We weren't sure that we could get a large cat underneath the conveyor belt that they had that they could not take apart. So we said, well, I don't think that that's going to work on, I think it was a 4.5-inch pile that they wanted to use. And we said, I said, I don't think that's going to work on that pile, but we're happy to do a load test. At the time, we were hoping to stop at 50 feet, which is why the 4.5 was kind of something that we were targeting. We ended up not being able to stop in a sand lens there. We ended up having to go much further beyond that, 118 feet, and it shocked us. It ended up being fortunate that they were doing some work nearby and we could bring a bunch of shafts out and weld them on. And we load tested the 4.5 and it didn't actually fail in settlement. So we did a full static load test. It didn't fail in settlement, but it failed in deflection. So the pile actually deflected under either the load was centric. We put the load directly over it because that was going to mimic the case. We think that the reaction frame had a very minor rotation and it was just so much load that it ended up deflecting laterally about 2 inches. So what we did is we went the next size up and we installed it, and then we made sure that there was a pile group like nearby, and then that was cast into the concrete floor. So we made sure that the load eccentricity wasn't going to be an issue. So hopefully that answers that question.
So Karam was asking, can you touch on the connection between helical piles and concrete pile caps or concrete beams? It's a great question. We do that all the time.
Yeah, so we offer like a modular cap. The common connection that we put on there, and the plate thickness depends on the load that's going to be applied. But let's say we're using a 4.5-inch pile. Like if you went with a 1/2-inch thick plate and then had 4 Nelson studs on it, or depending on the load, maybe a 3/8 plate, we put 4 Nelson studs on, just because that's an easy connection into the concrete that we see on a lot of commercial sites. Another common one is like an 8-inch piece of rebar, so 8 inches up and then about 8 inches out. So those are some of the common ones that we see.
And of course, Dale, sometimes those are bolted through or they will be a weld-on detail, but they do vary quite significantly. And we have also customized caps that also make it much easier or faster for people to do their form work. There's a couple of things that you might look at when designing a pile cap that would go on top of helical pile. From the folks at ASCII, just a terminology question, I think might have just been helical piles are quotation marks driven, which they're not driven, Dale, but
no,
something that we might say.
Yes. So what I said is that they're reacting similar to a driven pile in the high capacity format. So that's what I was meaning more on that side of things, that they're kind of replicating that relationship a little bit. Obviously, they're not driven. They're screwed into the till.
And then Karam had another question just about uplift load on the pile in cases where piles are encountering large uplift loads. Another great question.
Yeah, so the uplift is typically, like if we're using the torque equation, so this would be on smaller uplift loads, and we're using the torque equation, we usually go at about 75% of the torque equation. It's kind of funny because the torque equation was originally developed for the use of guy wires, and what Gelly and Hanna had done in the, I think, 89 or 90s, is that they'd installed 1,000 of these things and then they pulled them out of the ground. And some of them were single helical, some of them were double helical. and they would just basically get a big enough machine or a crane and they would just yank them out of the ground. So the 75% rule on the torque equation is conservative. We've done some pull tests on our piles and found that they end up far exceeding the expected values when we use torque. There's also a little bit of a function of depth, but I would say, I've been asked this before from engineers, like, hey, so as long as they're deep, they're good. And I was like, well, no, Winnipeg's a great example of that. Like, if you go 30 feet in Winnipeg and do a pull test on that pile, it might actually perform worse than if you've gone 15 feet because the soil isn't as dense. And depending on what the issue is, whether it's settlement that you're looking to avoid or if it's the ultimate capacity that you want.
Food for thought. I've worked on projects in northern Canada where soils were semi-permafrost conditions and piles were driven. To minimize the risk of frost jacking and add freeze in the freeze-thaw zone, we applied Arctic grease and wrapped the upper section of the pile with grease and cellophane. Yeah, that absolutely is a great.
This is where I see a lot of over-speccing being done, at least locally. We did a job for the Winnipeg Airport Authority where the original design called for a 7-inch, or maybe it was even an 8-inch shaft diameter. And then they had a large poly sleeve put on the pile. And then at the top of the pile connection was a welded plate. And then I was bidding on this project and I was saying, okay, well, our sales team was bidding on it and they came to me and they said, hey, what do we do with this whole poly sleeve thing? And I said, well, that should come out of that design. And they were like, well, really? Like, now we have to kind of go to the engineer. And I said, well, for sure. Like the helical pile, we went over the CAD freeze calculations to see that was I believe a double helical pile. And we checked it against the add freeze conditions. And the pile had more than enough resistance to accommodate the add freeze. The problem with the poly shaft was that I did some rudimentary calculations on that just to see how much force it was going to be applying to the plate. And it's at that point, it's for sure going to move because it's been designed to move. So it was going to put like an excessive amount of force on the bottom of the steel plate at the top of the pile. And when I brought that up to the engineers, they said, yeah, no, this is better without the poly sleeve on there. So I'd say permafrost is a different condition, but as part of that design, you'd want to make sure that you have some room for that sleeve to actually jack up and then be maintained by putting it back down so that it doesn't apply force on your structure. So
we're just about 5 minutes away here. Dale, maybe if you could, I'm sure that the wheels are going to be spinning in some folks' heads here. Maybe they have some questions afterwards that come up, or maybe they're looking at a project and they're just wondering if helical piles might be suitable. Sometimes helical piles are an option for performance, not necessarily an option for budget. And sometimes, it's the opposite, where helical piles can come in and save a budget. But if somebody wanted to get a hold of you to talk about that or to ask you a question, what's the best way for them to do that? I see it's on the screen, so I'm sure you're just going to point me that direction. But just wanting people to know that we're available.
Yeah, so I'll be reaching out to, I believe I have all of your email addresses. I'll be reaching out after this just to get a little bit of feedback and just see if you guys are comfortable where we landed on this and see if there's any further information that you need. Also, we're more than happy to collaborate on individual projects outside of this forum. Obviously, that may make sense. So feel free to reach out to me at the number. That's our main line number. If you can't get a hold of me, you can probably get a hold of Gary, and he's our sales manager. Or you can just email me at dale@versapile.com. I'd be happy to address any other questions that you have.
And we've certainly kept this fairly general for a general audience, but we are absolutely available to custom tailor a lunch and learn specific to your needs for your team as well. So if there's, lunch and learn, a certain perspective that you want covered in a lunch and learn in the future, please let us know. We'd love to put that together for you as well. And we can maybe put that together as another general lunch and learn, or we can do one specific to your team. And after this COVID-19, we'd love to do those face-to-face as well.
Yeah, it's a little bit easier face-to-face, at least for me. All right. Take care, everyone.
Thanks, everyone. Appreciate your attendance.
Thanks very much.